Okay, so we'll begin shortly. We're waiting for a few other people to join and then we start. My voice is audible to all of you, right?
Yes, sir.
Good. So I believe 2 assignments have been submitted so far in the course.
Yes, sir.
Okay, so we'll take both of them today. So your question 1 of assignment 1 was, with increasing height, the density and temperature. I mean, the answer is given, it should decrease. And I think in one of the session, last session, we answered this question. If anyone has any doubt, they can ask.
Sir, I guess this question should specify about the height. Till how much height? Because temperature then reverses, started increasing after tropopause.
Yes, you're right about that. So this question should specify about the height. Something like this happens. This is around 10 kilometers and this is around 20 kilometers. And most of the time, airplanes fly around here, 11 kilometers or 36,000 feet. So yes, you're right. Beyond that, we do not really worry much for the, especially for the aircrafts, but you can have high altitude aircraft that fly at maybe 40 kilometers. So this profile you can find out. And just a quick question. What is the atmospheric lapse rate? You know what I mean?
What
This is-
temperature, sir?
Huh.
From 0 to 10 kilometer, it should be 1.98 degrees Celsius per kilometer.
1.98
Per foot, sorry, per foot, per 1,000 foot.
per 1,000 foot. Okay. Okay, so in kilometers, it almost translates to minus 6.5.
Minus 6.9.
Yeah, per kilometer. Okay, in degree Celsius or degree or Kelvin, both. Okay, so this is the lapse rate. You start with some temperature on Earth, and you can find out the temperature in between from 0 to 10 kilometers, and beyond 10 kilometers up to 20, it's fixed. So I believe you understand the temperature profile. Yeah. We go to the next slide. Which airfoil is preferably used for design of horizontal and vertical tail? The answer is symmetrical, but we should know why. Anyone of you want to go ahead? Why should
Sir, because their main purpose is not to create lift
mhm,
initially. They need to make stable the
mhm.
aircraft. So there shouldn't be
Right.
any asymmetrical force unnecessarily if the air is coming straight ahead.
Very good answer. So there should not be any asymmetry in the force, because when you are flying, you might need to, let me start the pen. You might need to dive, you might need to climb, right? You might need to just, let's say you're moving that direction. So you might need to turn right, you might need to turn left, and you are not expecting any asymmetric forces. Let's say 5-degree, you have a, let's say beta, beta side slip angle. You have a 5-degree beta and you have a minus 5-degree beta, and you're experiencing, different forces. So your pilot will be confused how to fly this thing, right? So you want symmetry, and that's why you need symmetrical airfoils at the tail, both the tails, horizontal and vertical. So this was a easy question. Let's move ahead.
Wait. I
Yeah.
need answer for one thing. Can I?
Yeah, sure. Yes, sure.
Can you please drop positive cambered airfoil right now? Okay.
This is your
Actually, I just searched this answer na, so many figures I have found with this positive camber. That's why I have put a positive camber as my answer. But right now you are saying symmetrical. Oh, the answer is right. It is symmetrical. But why it should not be positive cambered?
I mean, you see, the question itself says preferably. It does not say exactly.
Okay.
So you will find on most aircrafts it's symmetrical.
Okay.
It's easier to balance with a symmetrical airfoil. But if you have a cambered airfoil, you can actually do calculations and do things combine in a certain way that you still get a symmetrical force, right? But then it's an extra burden with some advantages if you have for a cambered airfoil. All right.
I think, sir, maybe also there are a lot of images of airfoils of wing shape and which are positively cambered.
Okay. All right. So next question is wing loading will affect only stall speed, only climb rate. Answer is both. Now, most of you will know the answer why stall speed, because
Yes, sir. V star
you
equal
write
to W by S upon rho CL.
then
CL.
yeah. So
सर
this
एस
is
आपने ऊपर लिख दिया W by S में आप
oh yeah, right. And why climb rate? I mean rate of
the
climb.
climb needs more lift than
Mm-hmm,
in a level flight. So if
mm-hmm,
lift increases, the wing loading will increase as well.
right. So that's a good intuitive answer, but we still need to know the expression for rate of climb. So I have brought this. I brought something here. Yeah. So this is the figure of an aircraft. It is experiencing a thrust T in that direction. It's flying at a infinity with some angle U. So now the lift will be acting like this, and weight is always downwards. Drag is right behind the velocity. So this is drag. And so you can call it the force diagram, how the forces are acting on the aircraft. Now, if you are climbing steadily, if there is a steady climb, for example, Karthik is saying V sine U is the rate of climb, right? That's written here also. So now how do you derive this quantity V naught sine U uh, in terms of the forces that aircraft is experiencing? Because you have some information about the drag, lift, and thrust and weight, and you need this quantity. So in terms of forces, how do you arrive at this quantity V naught sine U? And on this side, I've denoted this U with theta, so it doesn't matter. It's just the angle. And so what you do a force balance along this direction, the direction of thrust. Can you do the force balance along the direction of the thrust and write down the equation? I'm expecting some answer like along the lift direction. I can do the balance. Let's say this is W, this is W cos theta. So what I can write is L is equal to W cos theta. Now my question is, please write the force balance along this direction, the thrust direction.
Sir, can I say the answer?
Yeah.
it will be T cos u plus L sin u equals to drag sin u and weight sin u. Here isn't drag, but weight sin u should be there.
I think all of you can see the chat, and Rohan has answered it correctly. Yeah, Rohan's answer is, I'll write it down here. Thrust is equal to drag plus the downward component of the weight, W sine theta in our case. So you do little manipulation. You write it as a T minus D is equal to W sine theta. You divide both sides with W and you multiply both sides with V infinity. So you get TV infinity, and that is exactly written here in this equation. Now, we already know that if aircraft is flying at a steady CL, you can write that CL from the lift formula, right? So this is the lift formula, and Q infinity is the dynamic pressure, half rho V square. And this is the CL, and the formula for drag is from the drag polar, and we can arrive at this expression for the drag when you substitute the value of CL in this equation for the drag. I'm assuming all of you know the drag polar, how we arrive at the drag polar. CL is equal to CD plus CD naught plus KCL square. This formula appears in most of the questions in assignment 1 and 2. You've seen that. So
Yes.
all, yeah. So then this is CD, sorry. This is drag, and you replace the quantities in this formula. This D, you replace the D from here and do some algebraic manipulations, and you will find out that the rate of climb is directly dependent upon W by S. So one of you answered correctly. When you climb, you require lift, and when you increase the lift, obviously wing loading is going to increase. And this is the analytical answer for your clarity, that yes, there is a formula that connects wing loading to rate of climb. Let's move ahead. The wing loading is given, maximum CL is given, and they're asking for Vstall. I think most of you will be able to answer this question, right? I just brought this formula in the last slide. I'll write it again. 2 WIS rho CL. CL is given, rho is given, 50 is WIS, everything is given. You have the answer. Find CL by CD max if drag polar is given like this. I believe.
Sir, in this question, they haven't mentioned the minimum thrust or minimum drag case. But the answer is given for minimum drag case. So they should specify that as well.
Okay, they've asked for this quantity, right?
Yes, sir.
Now, it can correspond to anything, minimum drag, minimum power, or whatever. It just so happens that it relates to minimum drag. So even if you don't know that it is related to minimum drag, this ratio, maximizing this ratio, you can still compute this ratio, right? All you need is this expression.
Yes,
and
sir.
Yeah, so if anyone has doubt in this question, they can ask. Otherwise I'll move ahead, because in the last session also we had taken few questions like this, and in this session also there will be few more questions like this. Okay, so maybe for everybody's clarity, we should tell what we are supposed to do. So you can do, this is your CD, you can divide it with CL, and since they are asking for maximizing it, then you can actually minimize CD or CL, just the opposite. So all you have to do is divide it with CL, and differentiate it with respect to CL. And whatever answer comes out, put it equal to 0. You will be able to solve for CL, and that will most probably be CD naught by K for this expression. If it's written like this, CD naught plus KCL square with CD. So your CD naught is this number, K is this number. It will probably come out this. Once you know CL, you can find out CD, and as a result, you know the CL or CD. Yeah, Achilles has written the right answer. Let us move ahead. An aircraft wing has a positive cambered airfoil. Which of the following graph correctly represents the graph between CL versus alpha?
It should be A.
It should be A. Okay. We know the right answer, then let's discuss the wrong answers. Why not this? What about B? What does B represent?
Because sir, it is a characteristic of a symmetrical aerofoil.
It's a symmetric airfoil. And why not C?
Negative
cambered.
Negative cambered. And how about the last one? I also don't know actually. What does it represent? It's
Yes, sir,
just,
because nothing can.
even if
generate-
you take a flat plate, it will have a different CL for different angle of attack, right? This is flat plate, it will have different CL for different angles. All right, let's move ahead. I thought that some of you might not know what exactly is the camber and positive camber. So this is the some airfoil, some random airfoil. It has two surfaces, the top surface and the bottom surface. There is something called mean camber line. Can you tell me the definition of mean camber line? Any one of you?
Sir, may I?
Yeah.
Sir, it is the difference between the upper part and lower part thickness. We can say it is the mean line dividing the upper half and lower half.
Say it again. I could not understand actually.
Sir, I am saying that it is the mean line dividing the upper half and lower half equally. It is
Okay.
equal distance to upper surface and lower surface.
Good.
Equidistant line.
Good. That's right answer. So if you go at every station, let's say these are different stations, you divide it in parts. Now you can divide it in infinitely many parts. And when you go here, you look at that point, you look at this point. Now, what is the point at the midpoint? So this is the midpoint. This is the midpoint. And if you find out all the midpoints and you connect the midpoints, then you get the mean camber line. Now, what is called the camber? What's the definition of camber?
Maximum distance between the chord and the main cam line.
Good. So this is maximum distance. It happens to be here, and that you call camber. Now, is it positively cambered or negatively cambered?
Positively.
When do we say it's positively cambered? All right. Usually we call this axis as positive axis, and that's negative axis. This distance is positive from the this chord. So you call it positively cambered. With the positive camber in aerofoil, alpha stall answer is decreases. Any one of you has explanation for that?
So flow separation will occur at a lower angle.
Flow separation will occur at a lower angle. Right answer. And I will just show you a picture. What happens? This is your symmetrical airfoil. Something called high lift device flap. It's usually at the back of the wing. When you deploy the flap positively, which is basically downward from the chord line, what happens is this entire wing can look like this. So effectively, camber changes positively. So camber is positive now. Now this CL versus alpha curve, it shifts towards that this direction. So it shifts this direction when you deploy it at different flap angles. So this corresponds to flap equal to -10. This corresponds to flap angle equals to +10 degree, and this is for zero flap, which is symmetric case. So you know this stall angle. It's here. In this case, it's here. In this case, it's here. So it's basically going towards zero. So it's getting reduced. And one of you said that separation occurs early. So you can see that even at zero angle of attack, the behavior is not symmetric, and it's about to, like, you can see the distance between the what you call these lines.
Streamline.
Yeah. So the distance between the streamlines is larger at the back of the wing. That indicates the vortices, existence of vortices and low pressure.
Excuse me, sir.
Yeah.
So I have a question. Will the characteristics of the a flat plate tilted at an angle alpha will be same as that of a symmetrical airfoil?
Yes. Theoretically, yes.
Okay.
We call it flat plate approximation. When we study aerodynamics, this symmetrical airfoil turns out to be similar to a flat plate. They both have a behavior like this for CL. So 2 pi is that number. They call it lift slope, and this is a theoretically predicted number. So no wing will have a lift slope greater than this. Which of the following statements are true for a typical flight of quadrotor UAV and fixed wing UAV? Answer is 4. For UAV, it's greater than 1, and for fixed wing UAV, it's less than 1. Now, for the fixed wing UAV, it's less than 1. How do we confirm that? Any test? Any confirmation test?
Sir, because sir, it is made for cruising, so it should not take too much of thrust for uh, going ahead. Instead, lift is created by the wings, so it reduces the weight part a lot.
I mean, that's I agree with your answer, but it's what to call it? It's a qualitative answer. I want test in terms of some formula, some numbers, confirmation test from whatever you understand. Can you verify that this number is exactly less than 1?
Sir, it mainly depends on in a fixed wing UAV. It mainly depends on the sign of the angle at which we are cruising or climbing.
Okay. Okay, let's take the cruise case because a fixed wing aircraft usually cruise. Now in cruise, tell me this number is less than 1. Just sit down, write down on your notebook something, and tell me.
Sir, lift is counteracting the weight and thrust is counteracting the drag. But drag is very much lower than the weight, we can say that. So thrust is greater. No, wait.
I'm reading the chat. Some answers have come from climb formula. If angle of climb is 90, then lift is greater than weight. I mean, that's fine, but we are talking about thrust to weight ratio. For forward, for FW, I don't know what FW means. The climb angle is small, hence the lift is less than the weight. That's also all right, but the thing is we are talking about thrust to weight ratio. And the question is,
So if the climb angle is 90, then the thrust has to be more than weight. That comes out of the climb formula itself. So in a fixed wing UAV, the climb angle is very small, so the thrust can be significantly lesser than the weight.
yeah,
In a
that's a
quadcopter,
special
you-
case when all of the weight is carried by thrust, right?
Yeah. But in a
Right,
quadcopter, to take off, your thrust has to be more than weight. That is the only condition at which it will take off, or it
Right.
has to be equal to weight.
right. Okay, Eva, I'll try. Maybe this expression will give us more confidence in the answer. Yeah. So few days back we were solving questions using this expression for cruise, right? This is only valid for cruise. So from here I see T over W is 1 over CL over CD. And for typical airplanes, CL over CD is maximized for design, basically for cruise. And this number ranges from 10 to 15. So if I put, let's say 10, it's 0.1. So you are only using 10% of the weight as a thrust. So here from here you can confirm the exact answer that yes, it's valid. And for quadrotor, I don't know who spoke, but they answered correctly. Usually quadrotors are like this. So when a quadrotor flies, all of the weight and all of the movement that is associated with the quadrotor, it comes out of the thrust. Let's say you have a weight W. So in hovering flight, every rotor will bear T/4 force. If you move slightly, and let's say you climb, then obviously you have to balance the weight, but you need more. You need acceleration force, and that acceleration force comes from the thrust only. There's no other way. So you obviously will have more thrust than the weight during climb or doing anything else. All right. The primary control for angle of attack is, the answer is elevator, and I think most of you will know the answer.
Yes,
Sir,
sir.
Yeah.
sir, I have a type.
Go ahead.
In a fixed wing,
Mm-hmm.
minimum drag condition was taken, and that's why it was less than 1. And in the quadcopter, y field is equal to 1 because thrust will be equal to weight when it will cruise.
Can you ask again, because your voice is echoing, so I could not make up exactly what you asked. I mean, can you speak again? Oh, he's writing. For quadrotor, y equal to 1 is not considered. And I don't know. I can see equal to 1 also. And there is nothing like cruise in quadrotor. It's powered flight always. There is no cruise. If you are in the air, you need thrust. All right, so I think this question should not give doubt to anybody. I'll just skip it. Which one is correct about static margin at neutral point of aircraft? Then what is neutral point? Anyone wants to give the definition of neutral point of aircraft?
Sir, a point which aerodynamic center meets the center of gravity exactly at the without no margins there. It is actually zero. There is difference between aerodynamic center and the center of gravity becomes zero. So that could be neutral point.
I think you're
Sir,
talking.
it is the point around which change in angle of attack doesn't vary the lift or drag created by the whole airplane.
I think you're close, but it's not exact definition. Anyone knows the exact definition for neutral point? Okay, so I'll have to teach you this thing. I'll take this topic, neutral point of aircraft, at the end of when we finish answering these questions, and then if we have time, we'll discuss about what exactly the neutral point is. But for the time being, the answer is simple. Yeah. So the neutral point is the point at which Cm alpha, pitching moment, derivative. Cm alpha, pitching moment slope actually. So this is slope with respect to alpha. This is 0. So what happens is, if you change angle of attack, pitch angle won't change. It remains there. You are at 5-degree angle of attack, you remains there. You're minus 5-degree angle of attack, you remain there. So when pitching moment is not generated, when you change angle of attack, this happens at the neutral point. Okay. Now, static margin is another quantity. What happens is, this is the fuselage center line. Okay. This is the, let's say, CG of the aircraft. And somewhere here, let's say, is the neutral point. Now, when aircraft flies, the weight of the aircraft changes. So the location of CG changes. And static margin is defined as a difference between the neutral point and location of CG. So neutral point comes from aerodynamics. Once you fix the aircraft, once you have an aircraft, you have a neutral point that is fixed aerodynamically. It doesn't change if you change the magnitude of the fuel, amount of the fuel in the wings, but CG changes along the flight. So when CG changes, the stability characteristic should not change too much. You want a margin for that. So what happens is, we know that it is guaranteed that CG will change when aircraft fly, and we want to make sure that stability characteristics do not change. They will change definitely, but they should not change too much. And to ensure that, we take this difference between the location of the neutral point and CG, and we keep it around like 15%. And 15% of what? Mean aerodynamic code. So 10 to 15% of distance it will always have. If aircraft is fuel empty, there is no fuel on board, in the wings, even then you will have like 15% of mean chord length between the neutral point and the CG. So the idea is, even if your aircraft is empty, it is stable aerodynamically. So that is the answer for this question. There are where is the leading edge of the wing? Yeah, I have not completed that drawing. Okay, I just wanted to give you a sense of these numbers. You can take anywhere. You can say that this is your reference point. You call it leading edge of the wing. Maybe your wing is like that. So you can measure these distances. Even they are not in the correct locations. CG is usually ahead of the XNP. Okay, so I know that. Don't worry, we'll discuss it at the end of this session. Now this is assignment 2, and the question 1 is, an aircraft is equipped with the symmetrical airfoil. For complete aircraft, the lift curve slope is given, stall angle is given, stall velocity is being asked, and wing loading is given, density of air is given for complete aircraft. So I think most of you can do this question. If anyone was not able to do the question, anyone has doubt in this question?
No, sir.
No. So I'll just go ahead. An aircraft has a wing area, its weight, and a drag polar. This equation is called drag polar, guys. This equation here, it's called drag polar. Aspect ratio is given 5, efficiency factor is given 0.85, compute L by D max. I mean, in the just last assignment, we did this question, right? CL at this condition will be CD naught by K, and this number is CD naught, and this number is K. So I think I should not focus too much on this question. Let's move ahead. What is CL at minimum drag? What is minimum
Under
drag
root
condition?
CD naught by, yes, sir.
What is minimum drag condition?
In which CL by CD is max.
Okay. So it's also minimum
Yes,
thrust
the minimum
condition.
drag, sir. Yes, sir. When parasite drag is equal to the induced drag.
Right. So when you have a T minimum, then you also have D minimum, right? So you know the condition for T minimum, you maximize this, and you can find out CL at that condition. So CL from previous question, whatever CL you found, you can use that as an answer here. Let's go to the next question. What is the velocity? So for velocity also you can do this. You have all the information about the aircraft. All you have to do is put CD naught by K here, and CD naught and K are given in the drag polar. So I think this question is also answered. If anyone has any doubt, they can ask, okay? Because these questions are getting repetitive, so I don't want to discuss over and over the same thing. This figure was given, and there are two questions. Point A represents the velocity for. Now this is point A. The answer is minimum power required. Why? Because this is the graph of the power, and this is the minima for power. So you can clearly see and tell that point A corresponds to minimum power required. Right? I don't think anyone has any doubt in this question. But how about this question? Point B represents to what? The answer is CL over CD max. Can anyone answer question 7? I'll write it here. Okay. And this is the location of point B. Did anyone get it correctly in the assignment?
No, sir. I did.
The point B is the point where the slope of this line is minimum. So it is the point where the drag is inherently minimum, because P upon V is directly proportional to D, because power required is drag into velocity. It's already written. So this point is a point where the drag is minimum. That will be CL by CD maximum.
That's correct. This is exactly the answer. The slope of this line, if you look at it, it's PR by V infinity. It's given also here, right? And when you this is D. Now, if you minimize this, so you minimize drag, and that gives you this condition, CL over CD, maximum condition when you minimize the drag. So thrust is equal to drag is equal to weight over CL over CD. That's how it comes out. You maximize this, you minimize drag. And now, why this is minimum slope? You can look at it this way. This angle is larger than this angle. This is, let's call it theta 2. Let's call it theta 1. So theta 2 is larger than theta 1. And if I look at this angle is also greater than this angle. Let's say theta 3. Theta 3 is greater than theta 1. So when a line originating from the origin goes tangentially to this curve, and that is the minimum slope, and that minimum slope corresponds to CL by CD maximum and drag minimum. If anyone has any doubt, still they can ask. All right, looks like everybody understood. 7 is clear. We are on 8. An aircraft has a gross weight of this. At the end of the missing segment, it has weight fraction as 0.85. Determine fuel consumed. So, I mean, how many of you got it correctly?
Yes, sir. I did.
Anyone else?
Yes, sir, correct.
All right. And is there anyone who got it wrong? Oh, nice. So the weight of the fuel, they're asking in kg. So mass of the fuel would be, I think, the gross weight. Let's call it mass gross. They're saying that weight fraction is 0.85. So that's the empty weight. All right. This is your answer for the fuel. An airliner with a takeoff gross weight of this much is cruising with fuel weight fraction 0.28. They're asking weight of the fuel in kg. Yeah. So I think most people also got it correctly, but it's just given. Mass of, let's call it G. So you see that almost 30% of the aircraft weight is its fuel. That's crazy. Okay. So what I thought is, because we have time left and we have nothing else to do, so we'll go through the basics of stability in the remaining time. Okay, because most of the people were not comfortable with those concepts, so we'll go through the concept of stability. Now in this picture, we are going to derive the contribution of wing to longitudinal stability. So in this picture, what you see is the flat line that you see in the bold, this line. This is an aircraft wing, okay, and this line is the fuselage reference line. So wing is mounted at some angle IW from the fuselage reference line, and the wind is coming in this direction, the relative wind. So the angle of attack is this overall angle alpha W. Okay. Now all distances are usually measured from the leading edge of the aircraft. So location of the aerodynamic center. Now there is a point aerodynamic center on the wing, and you should know the definition of aerodynamic center. It's the point at which the pitching moment does not change with change in angle of attack. So it's a very useful point. So what we do is we transfer all of the forces to this point, forces and moments. So what happens is there is a non-zero moment about this point, ACW. Lift is acting through this point, and if you visualize it correctly, the lift is perpendicular to the velocity, and drag is opposite to the velocity. All right. So lift and drag forces are acting on the aircraft wing, and this is the CG of the aircraft. Okay, and it has a Z location here, and its X location is this length. So this is our geometry. Parth Kapoor has asked, sir, aerodynamic center and neutral point are same. Yes. But neutral point, we talk in the context of the whole aircraft, and aerodynamic center, we talk in the context of any dynamic body. Right now, we're talking about the wing. When we talk about the aircraft, then wing and tail both are combined, and we call it neutral point. Also, you can say neutral point is the aerodynamic center of the whole aircraft. Okay. Now, my purpose to show you this picture and give you what I wanted to give here is your job is to write the pitching moment acting on the aircraft about CG. So you want to compute moments acting on the aircraft because of the wing about CG. So you want to compute moment about CG. How will you do that? You have only two forces acting on this aircraft right now. We don't have tail, only wing right now. So what you do is you decompose the forces. One component of lift is here. The other component is here. Same goes for the drag. One component of drag is here. The other component is like this, right? And then what you will do is, this is your point. Then for the vertical components of forces from lift and drag, this distance becomes the moment arm, right? So let's call it some force F1 times this moment arm. Let's call it some length L1. And for forces that are acting horizontally for these components, right? This length L2 becomes the moment arm. So all you have to do is add the remaining forces, let's say force F2, some L2. So what we are really doing is And also, of course, you have to keep the sign convention in mind, right? What kinds of moments are considered positive? Pitching up moments are taken as,
Clockwise.
yeah, no, anti-clockwise. Pitch up moments are taken as positive, and pitch down moments are taken as negative. That is just a convention. You can, of course, take opposite convention, and it won't matter. All right. So in the next slide, I'm going to show you the exact calculation of this moment. Okay. So here it is. So we had a force LW, and we took the sine and cos components of this LW, and I'll show you how it happened. The angle is alpha W minus IW. So which angle you need? You need this alpha with respect to fuselage reference line, because we are decomposing the forces along this fuselage reference line and perpendicular to the fuselage reference line. So for both forces, for the lift force and for the drag force, we need the angle from the fuselage reference line. So this is the angle we need. So if you look at the geometry, this angle is IW, and this is the alpha W. So this is the remaining angle, alpha FRL, and this is also alpha FRL. It becomes alpha FRL here for the lift also, right? So LW, and its cos component is upward, and its sine component is in this direction, forward. And for the drag, sine component is upward and cos component here, and you know the distances, right? What is L1 here? If I write L1, L1 was the distance between CG and this vertical line. So until here, the distance is XAC, and the whole distance is XCG. So L1 is basically XCG minus XAC. And how about L2? You can take it some number, let's say ZCG. So it's given to us. You write down the net moment acting on the aircraft about CG because of the forces produced by the wing, and which are lift and drag. You decompose the forces, you take moments, you keep sign convention in mind, and you write down this equation. Now, this is actual moments, and the dimension for this is Newton meter. It's actual torque if you talk about it. Now, how do I come to the coefficients equation? Pitching moment coefficients, lift coefficients. It's a coefficients equation, and this equation is in terms of actual forces and moments. How do I come from this equation to this equation? Anyone has any suggestions? How can we do that?
Sir, we will take some assumptions like alpha.
No. This is exact transformation. We're not taking assumption right here.
Dividing by Q infinity, C bar,
Yeah, what is that?
half rho v square C bar.
Right. Anyone else wants to answer and wants to confirm that this is right answer or wrong answer? Divide by dynamic pressure. Rohan has also confirmed that it is dynamic pressure. Right. So why dynamic pressure? Because usually what we do is the coefficients are defined in such a manner. Let's say this is lift force, and this is Q infinity, and this is area, and let's say CL. So how do you define CL? You define CL from lift force divided by Q infinity times S. And same goes for the moment. How do you define CM? Let's say your moment is M. So what you will do is Q infinity S. You will take a length also here, because pressure into area is what? Force. So force, both dimensions are same. This is a dimensionless number. Now moment, for the moment, the dimension is Newton meter. So force and length, Newton meter. So for the moment equation, you keep in mind that there is an extra C bar also here when we define CM. All right. So when we divide this entire equation by dynamic pressure and we convert these actual moments into coefficients here. So the C bar is appearing here, if you can see that. In the earlier equation, there was no C bar, but the C bar comes because we divided by C bar also, because we are neutralizing, we are non-dimensionalizing the moments and forces. All right. So the difference between these equations is nothing but the non-dimensionalization. If you look at LW, this is CLW. The cos component sitting right here, no change. This equation, since this is length, so we thought that we can put the C bar from here to here. So it's here. If you look at dW here, so CdW comes here. Only the length is divided by C bar. The sign is sitting right there. All right. So it's basic algebra, no change. Now we go to the next slide, and as we need to approximate things because it's a very complicated equation. It's hard to, I mean, do anything meaningful with these equations, right? So then we go to the next slide, and these are the approximations we make. So what we say is angle of attack is close to 0. So sine becomes alpha w, and cosine becomes 1. Then what happens? And this becomes the entire equation for CM pitching moment coefficient of wing with respect to CG. So this is the overall equation. Most of the terms got cancelled because of these two approximations. And yes, now it has two parts. If you look at it closely, we simply substitute CL is equal to CL naught plus CL alpha times alpha right here. Okay, and since CL naught is a constant, so now the equation overall has two parts. Things which are constant when angle of attack changes and the slope. So overall, this entire equation can be written as this: Cm naught plus Cm alpha times alpha. So things which are constant, whatever angle of attack you have, and this is the coefficient that gives us the impact of angle of attack change. If you change the angle of attack, this is the factor by which Cm is going to change. All right. So Cm is equal to Cm naught plus Cm alpha times alpha. Now this Cm naught has this value, and if you see that this number is constant, Cm of wing about aerodynamic center, and this is CL naught. It's also a constant number. It doesn't change with the angle of attack, and this is Cm alpha. Now we want to compute the contribution from the tail also. So before we go to the tail, we need to look at this picture. What kind of flow the tail is experiencing? All right. So if you look this picture, so there is an upwash region ahead of the wing, and there is a downwash region behind the wing. So this is the wing right here. Now, what happens when you have a downwash? The angle of attack changes, right? The local wind that the tail is experiencing changes because of this downwash. So when we take the forces and the drag that this tail is experiencing, when we compute those forces and moments, we have to consider that the angle of attack experienced by wing is different from what is experienced by the tail. So we will quantify that effect, the downwash effect. But before that, just like earlier, I want to show you this picture. This line is again the fuselage reference line. So we will use this line again to decompose the forces from the wing and from the tail. So for wing, it was very clear because we were looking only that half. Now we want to look at the remaining half. Okay, and also notice that earlier the velocity was coming like this along this line, but now the velocity has a downward component because of the downwash at the tail. So the tail is experiencing a different angle of attack. Keep that in mind, and by keeping that in mind, we write down the equation for the moments. Okay, I did not tell one more important number, which is LT. So since the forces that are acting on the tail are acting at the aerodynamic center of the tail, and remember, tail has a symmetrical airfoil, so that CM naught part will be 0 for this. Okay, CM AC part, sorry, CM AC part will be 0 for the tail. There is no moment at aerodynamic center for a symmetric airfoil. It comes out of the theory, so keep that in mind. Because for the wing, there was this number. I'll just go back and show you what number I'm talking about to give clarity. If you look at this is the total moment that we are having about CG because of the wing. Now it's because of the some component of the lift, some component of the drag, some other component of the lift, other component of the drag. Now this part is a fixed number. Now this number exists here because of the cambered airfoil at the wing, and this thing translates into the CMACW. But for the tail, there is no number like that. So for tail, this number is 0. CMAC is 0 because of the because it is a symmetric airfoil. So see that in our computations, while deriving the stability conditions, we are assuming that the airfoil is symmetrical, and that question which was asked in previous assignment was from here, because it is expected that you are studying from these books, and when you do stability analysis, you take the airfoil as symmetric. And I was talking about this number LT. So this number LT is the distance between CG and the aerodynamic center of the tail. So let's make it simple. There are two components that are generating forces. One is wing, one is tail. We want to compute the moments because of these forces about the point CG. So we need all distances of these forces from CG. So previously we decomposed forces vertically and horizontally. We'll do the same here, break the forces horizontally and vertically, then compute the moment arms. So moment arms, we need all moment arms. So the other moment arm is also given here. You can write down this. So basically, we have 4 distances: horizontal, vertical, horizontal, vertical. Both force generating components, wing and tail. Now there is one important thing here is I told you that the angle of attack experienced by tail is different from what is experienced by the wing. So how do we arrive at that angle? We'll discuss that also here. So when we write down the moments for tail, what do we have? We have, this is the one component of the force, that vertical component of the force, then LT, that distance. If you remember that, this LT is the distance between this vertical line and CG. So it's the horizontal distance, moment arm, if I can call it. Same for the drag, and then again for the drag and lift, and MACT. It's written here, but then it is 0. All right. So when we do the proper approximations, our final answer comes like this. Same approximations that we applied earlier. And this is the angle of attack experienced by the tail. Okay. So let's make it clear how we arrived at this answer. Okay, so this was IW. Wind was coming like this. This was alpha at wing. Okay. Now, this is the V infinity experienced by tail. This angle is IT. There is some downwash effect, epsilon. So what is happening here is, when you take this component alpha W minus IW, so alpha W is this whole angle minus IW, then you have this angle alpha from the fuselage reference line. Now, we know that air from fuselage reference line is this. So if you add the angle IT in the angle of fuselage reference line, then effectively you have this angle of attack. No down was considered. So what is the angle of attack at the tail? Alpha fuselage reference line for the wing, which was this number, alpha W minus IW. You add IT into it, and then you know that downwash is decreasing your angle of attack by some epsilon. So we will quantify epsilon also, but right now, consider this is the number. Now this is your angle of attack experienced by the tail, right? So anyone has any doubt in understanding what angle of attack tail is experiencing?
Clear, sir.
Yep, good. Now, similar as earlier, this MT, its actual Newton meter torque or moment. You need to non-dimensionalize it. So we divide with the dynamic pressure and the S and C bar also. So the coefficient form comes out like this. Now a ratio appears when, because LT and ST are sitting right there, and you non-dimensionalize it with the parameter with the dynamic pressure experienced by the wing. Remember that, with wing area and the mean aerodynamic code of the wing. So we are dividing it with the numbers experienced by the wing. Remember, during the non-dimensionalization. So this SC bar appears here. So this ratio appears. This ratio has a name. They call it, what do they call it? VH?
Volume fraction of tail.
Yeah, something like that. They call it volume fraction or volume ratio, horizontal tail volume ratio. So this, remember, this is a very important quantity while designing. People will tell you that what is the horizontal tail volume ratio of your aircraft. So this number, just substituted it here. So I'm giving emphasis on this number because this number is important for design. That's all. It's just a ratio. Remember its definition. LT is the, if you remember, LT is what? Distance between the aerodynamic center of the tail and CG. Aerodynamic center of the tail and CG, right? That distance is LT. ST is the tail area. S is wing area. C bar is the mean aerodynamic code of the wing. Now, this is this is some factor. This factor is included here because the dynamic pressure at wing, at wing is different from the dynamic pressure at tail. So let's say this neta is equal to 0.9. It means tail is experiencing 90% of the dynamic pressure which is at the wing. All right. So this is some sort of efficiency factor also included in this equation. And CLT is the lift coefficient for the tail. Now this when you substitute VH here, this expression becomes very simple. And now we are also clear about the angle of attack. So we can write it in terms of slope, since we know that the airfoil is symmetric. So CL for the tail part will be CL alpha tail times the angle of attack. We derived the expression for angle of attack already. So simply slope multiplied angle. This is slope and angle. And now we want to quantify this number, epsilon. How much the downwash effect? So this epsilon number is computed like this: epsilon naught plus this derivative with respect to alpha of epsilon times the angle of attack at the wing. Remember, this is angle of attack at the wing, because wing is the component that is generating downwash. Someone has asked something in the chat. My voice is echoing or what?
No, sir.
Okay.
For me,
Okay.
it is clear, sir.
Yeah, it's probably his network problem. All right. So now this epsilon has this expression, and when you take the derivative, then this CLW becomes CL alpha W. So it was actual coefficient of lift here, but it is the lift slope here. So you have expression for this. Now, what is number epsilon naught? This is downwash angle at zero angle of attack, and this is for other angles. So this is, you can call it, it's a Taylor approximation or first order approximation. You've heard these things in mathematics, right? So this is through Taylor approximation. You define a quantity at zero, you know its first derivative, and when do downwards changes? Because of angle of attack. So you take the effect of angle of attack through a derivative. So we approximate it like that. And these numbers come from aerodynamic and airfoil theory. These numbers, especially this number, it's derived in aerodynamic courses. So we use it as it is. All right. So now we have also quantified the contribution of the tail. Now we want to combine both and see what happens. Right. So in this slide, what I've done is we have substituted this number CLT. If you notice what was CLT, CLT had some alpha W, IW, epsilon, and IT. Notice this IW and IT, and within this epsilon naught, these are fixed numbers. These are constant numbers. When you are flying, they're not changing with angle of attack. So we want to break it down in two pieces. One is dependent on angle of attack, and other is independent of it, right? So when we take things, we separate things. So this appears constant with respect to angle of attack. Remember, it changes from aircraft to aircraft. For one aircraft, it will be fixed. Now, this number is dependent on angle of attack. All right. So this whole number, apart from this angle of attack, you take the angle of attack out, you call the whole quantity HCM alpha. It's written here. So this whole quantity CM alpha, pitching moment slope, contribution from the tail, and this is CM naught part, which is this constant part. So now this becomes the whole expression. What we have to do now is simply combine. So now look at this CM naught. This CM naught right here, it is coming from CM naught of the wing, CM naught of the tail. We know expressions for everything. We have CM alpha. Now it has also two contributions: CM alpha from the wing and CM alpha from the tail. We just simply add them. No hard mathematics, simple addition. Also, if you want to be very careful, you can have tail contribution also. Sorry, this fuselage contribution also, but it's hard to quantify it through some analytical expression. So in very basic analysis, you simply ignore CM naught F as 0. You can take it 0 and simply ignore it. But if you want precise calculations, you have some idea about the fuselage, the geometry of the fuselage rather, and the weight distribution, because it entirely depends on how the weight is distributed, right? And the geometry of the geometry of the fuselage. So it depends on both, right? So by knowing the geometry, you can compute the effect from fuselage. There are methods given, but for simplicity, you can ignore it in very basic analysis. So CM naught has this expression, CM naught from the wing, and this expression came from the tail contribution. This is CM alpha. This expression came from the wing, this from fuselage, and this from tail. Now, as I told you, you know the expression for CM alpha, pitching moment slope of the entire aircraft. You know this slope. Let's imagine a scenario when the slope is 0, right? When this slope is 0, what happens? Your CM remains fixed. Your aircraft does not experience any pitching moment. You leave it at certain angle of attack, it remains there. It's a bad situation, by the way. Okay, you want that your aircraft is stable. So usually what you want is your slope is negative. Okay, it's a negative slope in this curve if you look at it. And when you fly, you want to fly at this angle when CM is equal to 0. Overall CM is equal to 0. So you want to pitch the aircraft at a positive angle of attack. Okay, so that's for flying. And now, as I earlier told you, when the aircraft is flying, its CG is going to change. So what happens? The location of CG is changing, CM alpha is changing. Look here, the CM alpha quantity directly depends on the location of the CG, right? Now CG is changing, CM alpha is changing. It may so happen that CM alpha is 0. Now, if CM alpha becomes 0, your aircraft becomes neutrally stable. You cannot naturally, it cannot naturally stabilize itself. You have to pull the controls, right? Now, that situation happens, and beyond that, it's just unstable. It's bad. You pitch it positively, and then it'll simply go to the 90-degree pitch angle and just do crazy things. You don't want that. So you want CM alpha to go maximum at 0. It's always negative, but it goes towards 0 when CG changes. Now, one number that we discussed, we call that static margin, right? This static margin is kept because you want to make sure that you never reach that that point when CM alpha becomes 0. Now, I may ask you the question, what is that point when CM alpha becomes 0? So what you do is, you put is equal to 0 in this equation and solve for xcg. And instead of calling it xcg later on, you just call it np. It actually is nothing but xcg that corresponds to CM alpha is equal to 0. And you just call it neutral point, this number. So see, we derived this number from the aerodynamic characteristics of the aircraft. So this number is fixed for a given aircraft. If your wing is fixed, your tail is fixed, and fuselage characteristic is fixed, you know what is the neutral point for your aircraft, right? And now you can locate CG and you know, someone is pilot in our was a pilot in our session last time. Is he still here?
Yes, I'm there.
Yeah. Can you tell why they you know, they take care of weight distribution in the aircraft? Like, they don't want people to sit in the bulk in one area. They want to distribute the weight in some manner.
That is predominantly to adjust the CG. So if there is a CG limit for every aircraft, both the lateral and longitudinal. So most
Exactly.
aircraft
So that's
longitudinal CG, if it is beyond the limit, then you will not have any control margin there.
Exactly. And that's what we're talking about right now. CG is changing, right? So you don't want CG to go beyond a certain margin, and we call that static margin. So Rohan talked about this control margin, and we are talking about stability margin, and they call it static margin. All right. So I think I have given you some idea. You will only appreciate it when you go through the derivations yourself. I've taken all of these things from Nelson's book. So if you read chapter 2 of that book, you will have a pretty good idea about the stability, how to derive these equations, and detailed calculations also. There are some examples also, you can study those examples. I think I'm done with my presentation today. yeah, we have come at the end of it, but we still having time. So if you guys have any questions, I am happy to answer.
So can you go through the neutral point again?
Yeah, sure.
Thank you.
So what I'll do is, right. So wait. So the idea is, you derive an equation for pitching moment of the aircraft, and that's longitudinal pitching, right? Pitching is always longitudinal actually. So you write down the effect from all the components. Now this CM naught, it has contributions from wing, CM naught from the wing, CM naught from the tail, of course from the fuselage, and other surfaces if you have. But majorly you have these three surfaces. Then what you do, you derive components CM alpha from the wing, CM alpha from the tail, and from the fuselage. You just combine all of them. You arrive at this expression for CM naught and CM alpha. Now the idea is, an aircraft is cold stable when you change the angle of attack, but it goes back to the original angle at which it was pitched. So it was trimmed at. So usually when you plot this equation by changing alpha, this line appears on the graph. This axis is alpha, this axis is CM. Let's say we are flying at angle of attack 5 degree. By some chance, what happens if the wind gust from below hits the aircraft? What will happen to the angle of attack? Some aircraft is flying like this, and some wind gust hits the aircraft from the bottom. What is going to happen to the angle of attack experienced by the? I could not hear. It will increase, right? So angle of attack will increase. So you go to the angle of attack, which is, let's say, 7 degree. Now for 7 degree, you have a CM, which is obviously negative. CM is less than 0. Now tell me what happens when your aircraft is experiencing a negative pitch moment. Tell me the motion. What kind of motion the aircraft will execute? Can anyone tell me? Like, if your aircraft is experiencing a negative CM, what it is going to do? From whatever angle of attack it is currently flying at. Pitch down, right? So when you pitch down, so it goes from 7 degree to 5 degree, or maybe it'll go maybe to 4 degree. Let's say it goes to 4 degree because it doesn't stop immediately. So it will go past this angle and go to angle of attack 4 degree. But at 4 degree, what happens? It meets a CM that is positive. So naturally, if you have a positive pitching moment, your aircraft is experiencing a positive pitching moment, it's going to pitch up, which means it's going to try to increase the angle. So the angle will again increase. So the thing is, if you have trimmed your aircraft at alpha is equal to 5 degree, your aircraft will try to reject the effects from these perturbations, wind gusts, right? So you call it stable aircraft. Now, this Cm alpha, this slope does not remain constant. It's a fact. It's a fact because this Cm alpha expression, it contains a quantity xcg. This quantity changes when aircraft flies. And why it changes? Because we solved a question where the weight fraction was approximately 29% of the entire aircraft. So imagine you are exhausting, let's say 20% of that. You are exhausting 20% of the fuel of your aircraft. Your CG is naturally going to change. So your Cm alpha number is going to change. So what is going to happen is this slope is going to change, right? Since this slope is going to change, so the slope will look like this. So you have to pitch it probably higher angle of attack, and the let's say there is a slight change of angle of attack, then your aircraft will pitch up from here, but the rate of pitching up will be slower than it was in the previous case. All right, your aircraft is going to pitch up in this second case also. This is second case 2, this is case 1. In case 1, it rapidly tried to reject the disturbance. In case 2, it won't be doing that, because you see, you have to change the angle of attack quite large to experience a large Cm. So it will have very less amount of pitching moment. But at one point, what happens is this slope might become 0. If you change angle of attack, your Cm remains there. It doesn't change, right? It's always positive. So you cannot provide stability to your aircraft if Cm naught is positive. So you have constant pitching moment in your aircraft. It's called neutrally stable Cm alpha when it is 0. So what do? This is the limit of uh, this kind of stability curve. So you don't want to go there. So you name it something neutral point. You name it. The location of CG when Cm alpha becomes 0, you name it as neutral point. How to find that? You have this Cm alpha equation. You put Cm alpha 0 and then you solve for xcg in terms of the rest of the quantity. We did that calculation here. So this number is effectively xcg, location of the CG, for which Cm alpha is 0, right? I think it's clear for the person who asked this question.
Yes, sir. Yeah.
Yeah. Any other question?
Yes, sir.
We are still having like half an hour. Maybe next time I'll prepare more slides. And so what I'll do is, because these assignment questions are very few, like there are 10-20 questions. So we do that in within an hour. We still have 1 hour left. So I'll try to teach more things. I thought I will be able to cover it in 2 hours, but we did it much more rapidly, I think. So I'll just ask you people to ask questions, because we have to spend the rest of half an hour. You can talk about things that you're building also. Let's say if some of you are invested in some aircraft projects and maybe you are having some trouble, not having trouble, you can tell us your story maybe. No questions? All right, I'll wait for 5 minutes. If you ask questions, if someone has. Yes, these slides, they are probably shared with you. There is some public sheet, some Excel sheet, and that sheet has links for all the courses that NPTEL is running right now. They have sections like, we have made a folder on Google Drive, and that folder contains all these slides. I upload these right after this session. And for the videos of this session, also this same Google Sheet. That I don't know, assignment scores. I mean, they'll show you in the website also, right? Right? You have registered on some maybe that SWAM website. So I think it gives you that score. If it doesn't, I don't know. Yeah, Ron is saying scores are there on page. Okay, let's talk to people actually. Let's ask them where are they from and what do they work on. Let's start with Ron. Ron, where are you from and what do you work on? I think your mic is unmuted, but your voice is not coming. Yep, mic error. Let's go to Akhileshwar. Akhileshwar, where are you from and what do you work on?
Good evening, sir. I am from Bhopal, Madhya Pradesh.
Mhm.
Presently, I am a second year engineering student, BTech,
Which branch?
electrical and electronics engineering.
Electrical and electronics. Which college you are studying?
UIT RGPV,
Okay.
Bhopal.
And why are you interested in aircraft design course?
It's just sheer interest in me.
Oh, nice. And what other courses you have taken related to aircrafts?
I am also doing a course on NPTEL of lighter than air systems. And before this, in the previous semester, I had taken up engineering thermodynamics and introduction to aerospace engineering.
Oh, great. So you are interested in engines and flight also. Nice.
Yes.
And how about Ankush? Ankush is not going to speak. Reina Fatima. Where are you from?
Yes, sir. I'm from Kerala.
And what do you study?
Now I'm doing a diploma in data science.
Diploma in data science.
Yeah.
And how you got interested into aircraft design?
Sir, my dream subject is aerospace.
Oh, great.
Yeah, I'm planning to enroll for BTech in aerospace.
So, okay, after 10+2, you do diploma and then you want to go to BTech.
Yes.
Oh, great. Yes, Rohit is telling he's also from Kerala. Ripinder, I know he's from Amity. He's aerospace grad. Rohan is Pilot, he's also interested in this course. Who is PC? Rohin has done MSc in aerospace engineering. Right. So you did MSc, which means you had a bachelor's degree. From mechanical. Great. It's a good combination. You came from mechanical in aerospace. In the next session, maybe I'll take more slides and we'll teach you something that probably sir is not covering in his lectures, because I believe from what I've seen, sir's lectures are more. I mean, they are very direct and obvious. They're directly from the books, probably. So we'll also take books that sir has not considered. Sir has taken like Raymer, and he has also taken Anderson. We'll take some other books that are more modern. They have modern outlook in aircraft design. So I'll do that from next session.
Thank you, sir.
Yeah. You can buy books. I think buying books will be very expensive for you if you're a student. So you should find it out on internet. There are websites. Talk to people in your college. They know where to download the books from, and just print them. It'll cost you like 250, 300 rupees per book. If you buy it, if you find its Indian version, it will be cheaper. But if you are buying an international version, it's going to cost you more than 10,000 rupees. So buying is not a good option as a student. And probably your library won't have these books. So your best option is go to internet, find out how to download these. Every book is available on the internet. So you can print it. Yeah. Thank you, Rohan, for attending.
Thank you, sir. Thank you very much.
Yep. Good night, Ron. Thank you.